Hello everyone! Today we'll be telling you all about the heap data structure, covering what it is, the algorithms to create it, and which inputs each algorithm handles better than the other. To start, we'll cover the basics of what a heap is.
There are two types of heap, a min heap and a max heap. Heaps are partially ordered data structures, and these two types determine in which way the heap is ordered. A heap is conceptually similar to a tree with some additional constraints. First of all leaves must be on at most 2 levels. Second, all leaves on the lowest level are on the left. And all the levels except the lowest level are completely filled. Third, in the case of a min heap, the value of the root node is less than or equal to all of its children. And in the case of a max heap, the values of the root node is greater than or equal to all of its children. Finally, the left and right subtrees of a node are all, again, heaps. While all heaps are conceptually similar to trees, they are usually built on top of arrays. The left child of a node will be in position 2n plus 1, and the right child will be in position 2n plus 2.
We will now talk about the algorithms used to create heaps. The first we will discuss is called bubble up. Bubble up proceeds as follows. Each new element added to the heap is placed in the leftmost open spot in the array. The parent of this node is then checked. If the child should be in the parent's location, then the two values are swapped, and this process is repeated until a swap is no longer made. In this example, we will go over how the bubble up process will work. To start, the 10 is compared to the 7. As we can see, in a min heap, the 7 is exactly where it should be, so we move on to the next child, which is 3. 3 is less than 7, so we're going to change their positions. Next, we go to the first child of 10, which is 4. 4, once again, is less than 10, so we bubble it up. We now check 8 against 4, and as we can see, 4 is less than 8, so we make no swap. Next, we move to the first child of 7, which is 5. 5 is less than 7, so we make a swap. This is now a perfectly constructed min heap, made with the bubble up algorithm. Bubble up was the original heap construction algorithm. Because each level in the heap is filled, with the exception of the last level, the number of levels is limited to log n. In the worst case, every element entered into the heap will need to be bubbled up to the root by comparing and swapping each element with its parent repeatedly. The number of times an element is swapped up is limited by the height of the tree, which is log n. Since a total of n elements have to be processed, constructing an entire heap with this algorithm takes asymptotically big O n log n time.
The algorithm that has superseded bubble up to create a heap is the bubble down algorithm, which is more commonly known as heapify. This algorithm takes advantage of the fact that all leaves are single element heaps. It then combines every 2 leaves by comparing its parent to the smallest in a min heap or largest in a max heap, and then swapping the parent down if necessary. This creates 3 element heaps at the bottom. This process is repeated until this entire tree is joined in a single valid heap. In this example, we begin with the 2 leaves here, 4 and 3, which are heaps by themselves, and compare them to their parent, 7. Since 3 is the smallest child, and it's smaller than the parent, 7 gets swapped down with 3. On this right subheap, we only have 1 child, and it is smaller than its parent, so we make a swap again. Now we have 2 valid heaps, one with 3 at the top and one with 5 at the top. We join these 2 heaps again with 10. Since 3 is the smallest of the 2 children, it gets swapped with 10. 10 is still larger than one of its children, so it has to be swapped down again, this time with 4. The heapify algorithm handles almost all inputs more quickly than the bubble up algorithm. Asymptotically, it takes O of n time, since the bottom half of elements don't need to be moved. The next 4th, which is the next level, swap at most once with the level below them. Then the next 8th, which is the 3rd level up, swap at most twice with the levels below them, and so on. This mathematically comes out to linear time.
For certain inputs, the heapify algorithm will perform poorly. A small max heap input, for example, when min heapify is run on it, will make every level perform the most number of swaps possible. Because the total number of computer operations will be higher for heapify, where more comparisons have to be made for each swap than in bubble up, heapify will actually perform more slowly than bubble up, even though it is asymptotically superior. In this example, we have a max heap that has 1 as the root and 0 as each of its children. Because in heapify we are moving towards the leaves, we need to first make sure that the children nodes are actually inside of the array. In other words, that the node we are looking at actually has children. We then need to compare the two children to each other, and then compare the smaller of these two to the parent node. This is 3 total comparisons for one swap, whereas in bubble up, we only have to make one comparison for each swap, comparing 0 to 1, swapping them. In bubble up, we only need to make one comparison for each swap. Here, we compare the 0 to the 1 and see that the 0 is lower, so we switch these two. Once these are switched, we compare the other child node to this parent and see that they are equal, so no swap is made. In total, we made 2 comparisons and 1 swap, whereas in heapify, we had to make 3 comparisons for 1 swap, which is slower. Thank you for listening, and it was our pleasure to present to you.